So our last topic for chapter 8 is going to be about enthalpy. And enthalpy is really the heat of a process, the heat transfer of a process. So when we're talking about heat, we really mean enthalpy, because heat is a transfer, and enthalpy is really amount of energy, thermal energy that something has or something loses or gains. So in the process of a chemical reaction, all chemical reactions lose or gain energy in their process. We can't always pick up on that because we're not very good thermometers, but we can see that a chemical reaction does require some kind of change in energy in order for it to occur. And this is a whole section of chemistry called thermodynamics and thermochemistry. Specifically, thermochemistry is talking about temperature changes, like specific heat, the stuff that we've done in chapter 3. Thermodynamics talks more about whether or not the reaction will occur, and it has to do with the energy dynamics of the reaction. So when we're looking at enthalpy, we're going to use H as our variable. And don't worry about the conditions of constant pressure stuff. Like we're going to be using constant pressure for most everyday reactions. So this is more of a technical definition, but really you're looking for just the amount of energy that's lost or gained in a chemical reaction. So the enthalpy of reaction, and you may recognize this triangle here as a change. So the triangle means a change. So this delta, which is a delta, we've seen that before with Q equals MC delta T. So delta H of reaction means the change in enthalpy for the reaction. And so we can look at the number for that and tell if it is endothermic or exothermic, and you may recall those numbers or those words as well. So endothermic, meaning the heat is entering, and exothermic, meaning that heat is exiting. I don't want to use red and blue here because I don't want you to get confused with that. So exothermic is going to be a negative sign for my enthalpy because my system is losing energy. Energy is flowing out of the chemical system. I will feel it. My test tube will feel hot. The thermometer in the test tube will go up. So remember that if you're thinking about Q was also negative for exothermic. Turns out Q and delta H are essentially the same thing. They're measuring the same thing, which is just this transfer of thermal energy. So change in enthalpy is heat. It is that transfer. But enthalpy itself is the word we're looking for really when we say like, oh, that has a lot of heat, or that's hot or cold, like the thermal energy, that enthalpy, that's really the word we should be using. So energy flowing into the system, and this one I would feel the test tube as cold. So just kind of giving you a little bit of, so this would feel hot to me. Energy is flowing out of the system. And endothermic, energy is flowing into the system, so I would feel my test tube as cold, or my thermometer would decrease in temperature. So this is going to be positive, and if you recall, the Q was also positive for endothermic. So remember, it's not about how you feel, it's about what the chemical reaction is doing inside of your test tube or your beaker or wherever it is your chemical reaction is occurring. So kind of bringing our experience out of it and focusing on what's happening in the chemical reaction is really important to, grasping this concept. So remember that if you feel something get cold, that means it's sucking the energy from you, which means it's endothermic, pulling the energy from you, making you feel cold. If something you feel is hot, that means it's exothermic because it's releasing energy and pushing the energy to you. You are absorbing the energy. So make sure that you're always in reference to the chemical system, not necessarily what's happening with you. So just as a quick reminder of some of these graphs, we looked at these in chapter 3, but it's helpful to have a graphical analysis of this as well. What happens in an exothermic reaction is that your reactants are high energy, and high energy things are not very stable. They've got high potential energy, right? So like a weight at the top of the stairs, right? It's not stable. But then when it falls down, now it's on the ground, it's more stable. So if my reactants are less stable, higher energy, my products are more stable, lower energy, then I must have released energy on the way down, right? So that's exothermic. And then the other way around, if I have something that's more stable, like a weight at the bottom of the stairs, and I'm going to take the weight and put it up at the top of the stairs, I have to put energy in to do that. Systems don't just go from, if I push the weight off the stairs, I'm talking here about something, but let's just, okay, I have a weight. Let's use a kettlebell. If y'all do exercises, you'll recall this kettlebell if you've ever worked out with one of these beasts. So if I have a kettlebell or something up at the top of the stairs, and I push it down the stairs, it's gonna go down the stairs, right? I don't have to put in energy to get it to do that. I gotta put in a little bit of energy to push it, but then after that, oh, it's going, right? So that's like exothermic. But if I have a kettlebell and I have to take it up the stairs, like your trainer might have you do, you gotta put in energy to do that. So it's exothermic. So make sure that you are giving yourself multiple ways of understanding these concepts, because it's going to help you apply it to new systems. And drawings are always really helpful if you find something that works for you. I like to just draw the direction of heat flow if I'm not sure about something, but go back into chapter 3 and get some help with this if you feel like you're kind of forgetting or you're a little shaky on it. But for this chapter, we really don't have to be too heavy in the concept of it, really, because we're going to be using enthalpy as a conversion factor. So if I give you a chemical reaction like this combustion here, and I tell you the enthalpy of the reaction is negative, is that endo or exothermic? That's exothermic, right? Which means that heat is being produced. So where is the heat? If I were to like write the word heat in my reaction, where would I write that? In the reactant side or the product side? So heat is lost, given off, also produced. So hopefully you're thinking, well, if I have to write heat somewhere, I'm going to write that heat on the product side, right? So sometimes we'll write heat as a product, and you may have seen that in your oxygen lab if you had that lab. You may have also seen that in just any other, you're just researching some things, right? You may see people write heat as a reactant or a product. That means that this reaction produces energy, meaning it's exothermic. Well, how exothermic is it? Well, here's a measurement of this. This is the energy per one run of this reaction. So we can say this is the energy per one reaction. So as soon as I see that per there, I think, uh-oh, I have a conversion factor, so I hope you thought that. But the conversion factor is very customizable. So it depends on what substance I'm curious about. One run of this reaction will get you 802.3 kilojoules out. Now, keep in mind, can you have a negative energy? If you've taken a physics class before, hopefully you can kind of think about this. You cannot have a negative energy, right? So what does that negative mean? Remember, this is a change. So negative just means it's lost. So when I'm writing the conversion factors, I don't like to include the negative signs in my conversions because I want to understand that the negative sign only tells me direction. The sign tells me direction, meaning it tells me, when I say direction, I'm saying a direction of energy flow. So negative means energy is released, okay? I can also write released, energy released. And I should have wrote produces here. So if I'm looking to write a chemical using this per here, and I'm not going to write per reaction because the reaction is not anything I can do any math with. But I know that one reaction requires how many moles of methane? One reaction requires 1 mole of methane. So there we go. Can I say 802.3 kilojoules is equal to 1 mole of methane? Doesn't 1 mole of methane in this reaction produce 802.3 kilojoules? Absolutely. I could write this as heat, or I could write this as 802.3 kilojoules. Notice that I'm not writing the negative sign because the negative sign is not negative energy. Okay, the negative sign just tells you what side of the reaction your energy is on. So we will write sometimes heat, sometimes we'll give you the actual number in the reaction, and other times it'll be beside the reaction, or it'll be part of the word problem. It'll say like, hey, produces this much energy. So there's a lot of ways in which I can give you this information, but make sure that you are able to recognize that you can use it as a conversion factor. So let's write another conversion. Let's talk about our water. So how much energy is produced with 2 moles of water? Well, 2 moles of water is the energy, is the reaction amount, right? It's the one reaction means 2 moles of water are made, one run through. So essentially what we're doing here is we're just taking the coefficients, like a mole ratio, but instead of 2 substances, we're comparing energy to the substance. But that's just kind of like treating energy like it's a product, right? Like it's still kind of a relationship, it's a ratio. It's just that we're not using moles, now we're using joules or kilojoules or calories or other energy units. So there's a lot of information in one slide. Let's look at another slide where we have a different story. So here I'm giving you an enthalpy of reaction that is positive, which means that it is endothermic. So I'm going to write some descriptions of endothermic, and you can think about where your heat is going to go if we write it in the reaction. Let's see, so heat is entering, heat is used, heat is absorbed. These are all some terms that you might see to describe endothermic situations. So hopefully you have thought about it and you've decided to put your heat on the reactant side this time because it's absorbing, it's pulling the heat in or the energy in. So 182.6 kilojoules is what we can write, or we can write heat. And we have less to think about really with this positive. Just drop the positive or negative when you're sitting down to do ratio math with it. Now, if you're going to do Q equals MCAT work with these numbers, you need to keep the negative and positive because that's going to affect your temperature change. But with just describing this energy in terms of energy, they all have to be positive. So looking at let's just grab one conversion here. I'll just highlight the nitrogen monoxide. And I know that for every 182.6 kilojoules, I can make how many moles of nitrogen monoxide? Answer is going to be 2 because that's my coefficient. So hopefully you recognize a theme in using coefficients as ratios, and any information I give you about the reaction, we can relate that to the balance coefficients in the chemical reaction, which means that a balanced chemical reaction is a great tool for you. So make sure that you have your nomenclature down. When I say nitrogen plus oxygen creates nitrogen monoxide, that you can write and balance this reaction here. So let's give one last practice. So read through this question, go ahead and pause, read through this question, and see if you can come up with an answer. So hopefully you've read through and tried it. If you haven't, go back and do that before you watch me work it. So I'm given this enthalpy of the reaction here. Is this endothermic or exothermic? This is exothermic. How do you know this is exothermic? These are questions I'll ask you on an exam. I know this is exothermic because it is a negative, which means my energy is being lost, right? So I can think about my heat as a product, okay? All right, so let's see, 1.18 grams of propane. Stop. That I have something to do there, right? Hopefully you recognize that mass and you need molar mass. This is all the same stuff, y'all. We're just gonna do more different things with it, but it's like all the same ideas over and over and over again. So the repetition is good. So let's think about our molar mass. So 1 mole, molar mass is always 1 mole equals some number of grams. And I highly recommend that you get in the habit of writing it with these blanks, because it's just gonna help you find patterns and things and help you have something to write so that your paper is not blank and your mind is blank. It's got to get something down. Okay, so I know I'm going to have a molar mass here. So I want to know what's the heat in kilojoules associated with the combustion of all the propane in the tank. So how many kilojoules are equal to 1.18 times 10 to the 4 grams of this propane if I use all the propane? This is assuming I've got plenty of oxygen and I'm not limited by that. So they're saying here, if we use all the propane, that means my propane is my limiting reactant. So I really only need 2 conversions. I need a grams to moles, and I need a mole to kilojoule. And I know I can get that mole to kilojoule just by checking out my coefficient here. So let's write that conversion. So for every 1 mole of my propane, I know that's going to give me 2044 kilojoules. And I drop that negative sign here because I know I'm talking about energy units, and energy can't be negative. That negative sign is only there to tell me where the energy is going and the direction of the flow of energy, but it doesn't have value as a negative number for my energy production. Okay, so we need to fill in our molar mass, and then we can solve this thing. Hopefully you have already done this, and I'm sorry that I had not already done this, and I should prep my videos a little bit better to save you some time, but you can fast forward through if you need to, or put me on ×2 speed or something. Okay, so let's work this out. We have 1.18 times 10 to the 4 grams of propane. Notice that I'm still using my method of writing the unit and the substance. Even though I'm not changing substances here, it's just really good habit to have. So now I need my grams of propane to go on the bottom, and the number that goes with grams of propane is 44.11. It's equal to 1 mole of propane, and then one more conversion. Moles of propane have to go on the bottom. My conversion factor for this I get from my coefficient, which we don't write ones in chemistry, so nothing in front of the substance means 1. 2044 kilojoules. And if I asked you to give it to me in joules, then you would have to do an extra conversion, right? Or calories, if I gave you a joule to calorie conversion. Use the periodic table equation sheet for any of those kind of conversions, but I will give you anything that's not on that sheet if I'm expecting you to do something. I'm not expecting y'all to memorize molar masses or anything that's not on the memory sheet that I give my classes. I don't expect y'all to know anything that's not on that sheet. as far as memory goes. Like there's a couple of things, maybe like your covalent stuff, but no numbers or constants that aren't on that memory chart. All right, well, that's a lot of kilojoules, and I'm asking you for kilojoules, but if I wasn't asking you for kilojoules, this may be a number where you decide maybe you want to give this answer to me in, a different, like a megajoules or something like that, right? But we're trying to convey probably the amount of energy I get from a tank of propane. And I hope I get a lot of energy from my tank of propane, right? So I'm talking about the whole tank. And it is indeed that we have a lot of energy from this, but I need to narrow this down with my sig figs. So I need 3 sig figs. Now I can use this, this number, if it's given to you, probably does not limit your sig figs. So we're kind of in the point of our sig fig lives where that, remember I've told you before, 95% of the time, the amount of sig figs in your given is the amount of sig figs in your answer. And there's a few exceptions to that, but really we kind of throw that away in chapter 2. And once we move on to more complicated math, I'm trying to make your sig figs a little less complicated. So I'll probably only give you numbers to where even if you did include the numbers in your sig fig calculations, they're not going to affect it. So I really wouldn't include numbers that I could look up like this, numbers that I'm given on my periodic table, as indicative of sig figs, because they can be found with more significant figures. I can go look this number up for the propane combustion to many more sig figs after this. So just now is probably a good time to say, well, the number of sig figs in my given is probably the number of sig figs in my answer. So if I want this, can I say 547 kilojoules? I hope that you are shaking your head, yelling at the screen, telling me, no, you can't do that. Why can't I do that? Because this is 546,796. If I owed you $546,000 and I gave you $547 because sig figs, we're not cool. You better be yelling at me because I owe you a lot more money. So we have a few options. I can always just throw some zeros behind it. Isn't that 3 sig figs? And isn't it still 546,000-ish? Sure. Or throw this thing in scientific notation. Just throw it in scientific notation. If I need to move, let's just do a review really quick. I need to get my decimal right here. 1, 2, 3, 4, 5. So this is going to be 10 to the positive 5 because it's a big number. Told you in chemistry, we build. We never leave anything behind. So it's good to review. All right, hopefully you have that kind of down. If you've got any questions, please text me and ask. And I hope that this has been pleasant for you and not terrible. See you later.